All right, today we're going to take a look at buffer solutions. Buffer solutions are made up of a weak acid and its salt would contain its conjugate base. Or it would be comprised of a weak base and its salt. And the salt would be comprised of the conjugate acid. So if we had HCl, well, this should automatically tell you HCl is not a weak acid, so it won't work. HCl is strong. So if we had HCl and Cl minus, or a salt would have NaCl, because if you dissociate it, it would have Na plus and then Cl minus. Cl minus would be the conjugate base. This would not work because it's not a weak acid, but I wanted to put that out there for you. So what could it look like? If we had HF, hydrofluoric acid, and then its conjugate base, it would have to contain F minus. Then we take a look here. So we could have NaF, which could be a salt because it dissociates, it's soluble, and then you would make Na plus F minus. Or you could have Kf, which would be dissociated as K plus and F minus. So the presence of the weak acid and its conjugate base would make a buffer solution, as long as you had initial concentrations of both of those. And the salt would dissociate. So if you had HF and NaF, or HF and KF, for example, then you would have HF and F minus, and then that would be a buffer solution. Weak base could be ammonia, NH3. So then that means that the salt would have to contain the conjugate acid. The conjugate acid would be NH4 plus. We could have NH4Cl, because that would dissociate into NH4 plus Cl minus. Cl minus would be the spectator ion, and then NH4 plus, well, hey, that's the conjugate acid. Or we could have NH4Br, and then that would make NH4 plus, and then Br minus. And then we would once again have the weak base and its conjugate acid, or a weak base and its salt that we have here. So initially, as long as you start off with concentrations of both of those, or both of those, you would have a buffer solution: weak acid and its salt, weak base and its salt. We're going to now calculate the pH of a buffer solution, but it's actually quite simple based on what we've done before. Here's our problem now for the pH of a buffer solution. Calculate the pH of a solution containing, now this is different because normally we would only have a weak acid or we'd have a weak base. So over here, let's take a look. We have a weak acid and then we have its conjugate base. We're going to go ahead and write the ice table. So we can write the dissociation equation for HF. So HF, double arrow, H plus F minus. And then we'll set up our ice table. On the I line, we have HF. So we have 0.300 molar. Initially, we have no H plus. And then now initially, remember the NaF will dissociate into Na plus and F minus, and the mole ratio is 1:1. So really, we have 0.200 molar F minus initially. So we'll put that in here. Our ice table, so we have no H plus, so this should be a plus X. This should be also a plus X since they're on the same side and it's a 1:1 mole ratio. And this would be minus X. And then we end up with 0.300 minus X. And then we get plus X. And then we get 0.200 plus X. All right, now all we have to do is then we set up the Ka expression, just like we've done before in the past. So we take the concentration of H plus times the concentration of F minus over the concentration of HF, and we plug and chug. So I looked up on the internet the Ka value of HF, which is 6.6 times 10 to the negative fourth equals, and then we take the X for the H plus, and then for F minus we have 0.200 plus X over, and then for HF we have 0.300 plus x. So now what we can do is, instead of doing the quadratic equation, we can do like we would with the 5% rule. So we'll just get rid of the plus x. And sorry, this was a minus x over here. We can get rid of the minus x that's attached to the number. This number x by itself is super small, so we have to leave that by itself because that's what we're trying to solve for. So if we go ahead and take 6.6 times 10 to the negative fourth times 0.3 divided by 0.2, we get x equals 9.9 times 10 to the negative fourth molar. And then this would equal the H plus, because that's what we solved for here. Now the last move, just like we've done before, so pH would equal the negative log of the concentration H plus. So pH would equal the negative log of 9.9 times 10 to the negative fourth. And then we happen to get 3.004. And then that would be the pH of this buffer solution. Now let's go ahead and take a look at something else. So now in the setup, what I changed is I actually changed the concentration of NaF to 0.300 molar. So what that's going to do is, let's change the concentrations here for F minus to 0.300 molar, and the concentration F minus at equilibrium to 0.300 plus X. So now that's done here. And then so that makes that so that this would be 0.300. And then what happens is we end up with 6.6 times 10 to the negative fourth times 0.3 divided by 0.3. So X equals the Ka. And then we just negative log the Ka. So negative log 6.6 times 10 to the negative fourth. And we get 3.180. Now what I wanted to show you was, okay, I know I went through this quickly. All right, the concentrations at HF, which is the weak acid, and the concentration of the conjugate base are now equal. So in the ICE table, we set it up, they're equal. And then we end up with 0.300 plus X and 0.300 minus X over here. But what happens is over here, these are equal, and then these will cancel out because they're the same. And so what we have here is then the Ka value is equal to the concentration at H plus, and we negative logged it. So what happened here? By having weak acid and its conjugate base, it allows us the maximum buffering capacity. So if we added base, like hydroxide, to this buffer solution, what part of the buffer would be neutralized by adding hydroxide to it? Well, if you said HF because it's an acid, it would get neutralized by adding base. Then what's going to happen is this concentration will get neutralized, and then we'll make some conjugate base. And then vice versa, what if we added H plus ions to this, like acid, like HCl or HBr? Which part of the buffer solution would neutralize it? Well, if you said the NaF or the F minus would neutralize the H plus, then that's correct. And then so what happens is, when we have equal concentrations of the weak acid and its conjugate base, then we have the maximum buffering capacity. And in this part, the pH would equal the negative log of the Ka, which is also known as the pKa. All right, the last thing is, well, how do we get pH equals pKa? I'm going to show you a shortcut that's not necessarily needed to be memorized for the AP exam, but is also helpful. It's a shortcut for calculating the pH of a buffer solution called the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation only helps you calculate the pH of a buffer solution. So we have a weak acid and we have its conjugate base. The equation looks like this: pH equals pKa plus the log of the concentration of the base, the conjugate base, over the concentration of the acid. And the way to remember it is, since it's pKa, the acid should go on the bottom, just like on the equilibrium constant. So if we take a look here, you can also practice with the original equation that we did with the different numbers like 0.300 molar and 0.200 molar. We take the pKa, so P in pH is negative log, and then the Ka that we had from before was 6.6 times 10 to the negative fourth for the Ka of HF. So we'll put that in there, plus the log of the concentration of the base. So that's the F minus. So that's 0.300 divided by the concentration of the acid that we're given, which is 0.300. So if we take this, 0.300 divided by 0.300 is basically the log of the number 1. And remember, the log of 1 is equal to 0. So in this case, pH equals pKa. And then so we have pH equals the negative log of 6.6 times 10 to the negative fourth, which we already figured out was 3.180 from the previous one. So this is also another way of calculating the pH of a buffer solution. Which way is acceptable on the AP exam? Both are acceptable. Nice table or the Henderson-Hasselbalch equation, whichever one you choose.